In this video, we're going to look at how to graph polynomial functions. Specifically, we're going to look at the end behavior of polynomial functions. So we're not going to be super detailed, but let's jump into it. And first, let's start with a definition of polynomial functions. And so polynomial functions take this form. Now, don't let this form confuse you. Just look at a sub n and a sub n minus 1 and a sub 1 and a sub... Look at those as coefficients. These are just numbers, okay? And then notice your exponents are decreasing as you move from left to right. N minus 1, next would be n minus 2, n minus 3, until you have a 1, and then you have an x to the 0, which wouldn't really be there, it'd just be a 1. So let me, just to throw an example out there, that'd be like 3x to the 4th minus 2x squared plus 8x, or 8x to the 1st, because we have a little first there, plus a constant, or I could even say minus a constant. That would be an example of a polynomial function. These exponents are going to decrease. Now, you don't have to have every single number. I don't have to go from 4 to 3 to 2 to 1 to 0. But in general, you have your largest exponent, and then it's going to go down. And these are all, here we go. This is important. The degree of the polynomial function is the highest value for n, where a sub n is not equal to 0. So this particular polynomial will be a 4th degree. If I were to erase that, then all of a sudden we have a 2nd degree polynomial. So know that. And then know that n is a non-negative integer. We don't have fractions in our exponents. You can do that. You can graph that, but then it's just not considered a polynomial. But where we really want to live is right here, because this is going to be our important thing. It says the end behavior of a polynomial graph is determined by the dominating term, which is a cool name for this guy right here. So in my first example, or I'll make up another example, if I had negative 2x to the 5th plus 3x to the 3rd minus 1/2 x squared plus 7, then this term right here would be considered the dominating term, and it controls what the end behavior would be. So what you need to do, if you haven't done this yet, is watch my video over end behavior of power functions, because you need to know that before you know where we're about to go. So it says, backing up, it says predict the end behavior of this polynomial function. We see it's a polynomial function, so the first thing we're going to do is we're going to identify the dominating term. And this right here is our dominating term, okay? And so what's going to happen is, based on that, our end behavior is going to fall in one of 4 categories. It might look like this. It might go up on both sides, and I guess that should be a little bit more accurate. It could go up on the left and then do a bunch of weird stuff in the middle and then go up on the right. You know, in here you could have all sorts of stuff like that going on. And then it could go down on the left and then do some weird stuff, and then go down on the right. You could have that function start down and to the left, but then after it kind of does its wiggling and wobbling, it goes up and to the right, and then we could have our reflection of that. Those are our 4 categories, okay? And when these occur is, this first one occurs when the exponent is even. This occurs when the exponent is odd. And this happens when the leading coefficient is greater than 0. I'll just say a is greater than 0 because that's what we normally use for it. And this happens when our leading coefficient a is less than 0, okay? So just by looking at this, we should see which of these 4 categories does this particular polynomial function fall in. So if I look at it, what we have is we have a negative leading coefficient. So we're down here with a leading coefficient that is negative, so it's going to be one of those 2. But then what we have whenever I look at the exponent is we have an odd exponent, which if I come up here, we have an odd exponent. So what we know is our function is basically going to look like this. I don't know too many details at this point about how steep it is, what happens in between, but the end behavior is that as we go to the left, it's going to increase, but as we go to the right, it's going to decrease, okay? So based on that, I'm going to go to the next slide, and I'm going to have you just kind of draw rough sketches of a few examples. So as we look at this, here's 4 examples. I would encourage you to pause the video and try these on your own, but I'm just going to jump into it. So here's our dominating term right here. We have an even exponent on it. So that means our function is going to have matching end behavior. It might go like this, or it might go like this. Okay? Since that leading coefficient's positive, our function is going to be increasing as we go to the left and increasing as we go to the right. Now, there's could be all sorts of stuff happen in the middle, but that's what our end behavior would look like. Okay? Next, as I look at this one, we still have the even exponent, so we got that matching end behavior, either that or that, but in this case we have a negative leading coefficient. Since we have that negative, specifically a -1, we know that our function is going to decrease as we go to the left, and then some stuff's going to happen in the middle, and then it's going to decrease as we go to the right. In our third example, we now have the odd exponent. So if we have the odd exponent, remember our end behavior is going to be opposite. It might go down one way and up on the other, or it could go, it could start high, and then as x increases, it ends low. We don't know, but that's what the odd exponent tells us. And since that leading coefficient is a positive, that means it's going to be this one, okay? And then lastly, in our last example, it looks like we have the odd exponent again, but the negative leading coefficient. So this particular function is going to do this number here. It's going to start high, and then it's going to do some stuff, and then it's going to end low. Now, to be specific, I just want us to understand, we're not saying that these numbers don't matter. All these other values in the function are important, and we're going to learn more about what they do in subsequent videos. But for now, we're just looking at the end behavior, and the end behavior is controlled by the dominating term. So we're going to look more at how these other values affect our function later, but for now, what happens on the very left end and on the very right end is controlled by that dominating term.